All right, guys, good morning. This is our final day of new content in AP Chemistry. So today we are going to talk about electrolytic cells and Faraday's law. All right, so basically an electrolytic cell is a galvanic cell running backwards. So while a galvanic cell runs on its own and it runs backwards, is thermodynamically favorable and runs on its own, produces electricity. Electrolytic cells don't. So they are non-spontaneous. So that means our cell potential is negative, and we have to add electrons from an outside source in order for this reaction to take place. So we have to have a battery or something in order for this reaction to take place. So this results in the conversion of electrical energy into chemical energy. So in a galvanic cell, we take chemical energy and turn it into electrical energy, but in a electrolytic cell, we need to have that, goodness, why I'm totally struggling. We have to have the electricity to cause the reaction to take place. Examples are electrolysis of water, salt solutions, and or silver plating something. So electrolysis is where you basically run a current through water and it causes the water to break down into hydrogen and oxygen, things like that. So this right here is an example of plating. All right, and basically right here we have that current running through our solution and it causes our copper to be plated onto our key in this example. Now, I do want to kind of talk through some of the big differences between galvanic and electrolytic cells because, again, mostly solving these electrolytic cell problems is going to be the same as solving galvanic cells, but instead of looking to get a non-spontaneous or a spontaneous reaction, we're trying to get a non-spontaneous reaction. So our galvanic cells are thermodynamically favorable reactions. Electrolytics are unfavorable reactions, so they won't happen without the addition of electricity to make them happen. Anodes and cathodes are in separate chambers in galvanic cells, so we have those half cells. Each reaction is a half cell, whereas in electrolytic, they are in the same chamber. We have to have a salt bridge in galvanic cells. We have no salt bridge in electrolytic. No power source needed in galvanic, but we do need a power source for electrolytic. And then galvanic produce electrical energy, and electrolytic use electrical energy. So in both, so that could be some things that you could potentially see if a test question shows you a diagram. Looking for these differences could help us figure out, is this electrolytic or galvanic? You know, specifically looking for that power source and then being in the same chamber is going to be a really good clue that that's an electrolytic reaction going on instead of a galvanic reaction going on. Now, there are some things that occur in both. So at both, oxidation occurs at the anode and reduction occurs at the cathode. They also do still both require an ion flow in the cell for our reaction to actually occur. So that kind of highlights a little bit of the differences between galvanic and electrolytic. Again, solving most of the time, if you are asked for to solve for E-cell or anything like that of an electrolytic, be the same concept, but instead of flipping our reactions to get a positive value, we would flip our reactions to make sure that we got a negative value for our cell potential in an electrolytic cell. Okay, so now what we're really going to focus on for the rest of this video is, so electrolytic is also can be called electrolysis, but what we're going to look at is really Faraday's law, but really kind of more than that, this is the stoichiometry of this unit. So Faraday's law tells us the amount of substance being oxidized or reduced at each electrode during electrolysis is directly proportional to the amount of electricity that passes through the cell. So we are actually going to be able to figure out how much stuff is being plated or produced based on how much electricity is flowing through it. And we're going to use stoichiometry. So we do need to know a few things in order to do that. And the first thing we need to know is, what is a coulomb? So a coulomb is equal to an amp times a second. This is the amount of charge that passes a given point when 1 amp of electrical current flows for 1 second. So amps times seconds is coulombs. Then an ampere or an amp, is a flow rate of 1 coulomb per second. So this is just like how fast my electricity is flowing, and it's 1 coulomb per second. I is often used as a symbol for current, which ampere is a measure of current. So we would see that pretty often, as well as I. And joule is the amount of energy absorbed or evolved when 1 coulomb of electrical charge moves through a potential difference of 1 volt. Cool. Okay. So there are some conversion factors we would need to know. All right. Amps times time equals coulombs. And there are 96,485 coulombs in 1 Faraday. Guys, that number is on your formula chart for AP. 1 Faraday equals 1 mole of electrons. And then I equals Q over T. So I is our current in amps, and Q is our charge in coulombs, and T is our time. So I equals Q over T. So we will use dimensional analysis to help us solve these electrolysis problems. And this is kind of what it's going to look like pretty much every time. So current is going to be amps times. So this is kind of like a basic formula. So it kind of depends on what you're starting with and what you are given, because it may give you different things each time. So a lot of times we may start with current, which is amps times time, and convert that to coulombs. Then we're able to convert coulombs to Faradays. Then we're able to convert Faradays to moles of reactant. And then we're able to convert that to grams of reactant using those conversion factors that we just talked about, that there are 96,485 coulombs in 1 Faraday. 1 Faraday is 1 mole of electrons. We'll be able to use those in order to convert from one thing to another. All right, and then if it's flipped, obviously we would do it backwards. So grams of reactant to moles of reactant to Faradays to coulombs to current, which is amps, times time. All right, so let's look at this first one. So this one says, how many grams of chromium can be plated by passing 2.05 amps through acidic CrO3 for 1 times 10 to the 4th seconds? So basically, first thing we need to figure out, though, is what is our reaction here? Like, what is happening? And so we have this CrO3, and we are going to need this for one of our conversions. So the CrO3, oxygen always has a -2 charge. Chromium has a +6 charge. So that means I am starting with chromium +6. And I want it to just turn into chromium. I want it to just turn into Cr. All right, so that means that it is gaining 6 electrons. And since it's gaining, this is an oxidation reaction. So to go from an oxidation number of +6 to 0, 6 electrons must be gained, and this would be our reaction. And we are going to need that right there. All right, so we are passing 2.05 amps through that for 1 times 10 to the 4th seconds. Now, this 2.05 amps is going to be one of our conversion factors. And remember that amps is coulombs times, basically coulombs per second. Yeah, so amps is basically also another way we could say this is coulombs per second. Okay, so we're going to start with this 1 times 10 to the -4th seconds. 1.0 times 10 to the -4 seconds, because that's how long we are running our current through. Now, seconds is not what we want, so we're going to drop it low. This is where we can use that amps here. So I know that for every 1 second, 2.05 coulombs pass through. All right, so for every 1 second, 2.05 coulombs pass through. Now I can start using those other conversion factors that we've learned. So there are 96,485 coulombs in 1 Faraday. So there are 96,485 coulombs in 1 Faraday. And 1 Faraday is 1 mole of electrons. So just those two conversion factors that I got from the previous page on my notes. So 1 mole of electrons is 1 Faraday. All right, now guys, we are trying to get to chromium. And so essentially what we're going to do here is kind of our mole to mole ratio. All right, and in my reaction, I have moles of electrons. And so from my reaction, I know that for every 6 moles of electrons, it's going to make 1 mole of chromium, of that Cr. All right. And then from there, so now we're in moles of Cr. So now all we need to do is use the molar mass to get to grams. So 1 mole of chromium is 52.0 grams of chromium. And we just pull that straight from the periodic table. And then we're just solving. So multiply across the top, divide by the bottom. So, really, hopefully this isn't too bad. So multiply across the top and then divide by the product of the bottom. And we'll just use our dimensional analysis / our stoichiometry to be able to solve these problems. So go ahead, take a second and plug it into your calculator. And when I plug it in, I get that my answer is 1.84 grams of chromium. So you can see we started with time, and then we used our current, and then converted from coulombs to Faradays, Faradays to moles of electrons, and then used our chemical reaction of saying for every 6 moles of electrons, you can make 1 mole of chromium, and 1 mole of chromium weighs 52 grams. We get 1.84 grams of chromium as our answer there. All right, so we have one more problem. I want you guys to pause the video. This one is backwards from the previous one that we did. So I want you guys to go ahead and pause the video and try to work this one out on your own, and then restart the video so we can go over it as well. All right, so go ahead and pause it. Okay, let's go over it. So we see, and this one is asking how many hours would it take to produce 25 grams of chromium from a solution of CrCl3 by a current of 2.75 amperes. Okay, so first thing we need to do is we need to figure out our oxidation reaction here. So I have chromium +3, all right, because I have Cl has a -1 charge, I have 3 Cls, so that gives my chromium a +3 charge. And I want to end up with just plain chromium. So that means that that chromium +3 is gaining 3 electrons to become chromium. So this is my oxidation reaction. All right, I'm sorry, my reduction reaction. Reduction is gain of electrons. I have no idea why I said oxidation. Okay, cool. So then I'm going to take my 25 grams of chromium. So 25 grams of chromium, all right, is my starting point. And I'm going to convert from grams of chromium into moles of chromium. From moles of chromium into electrons. So for 1 mole of chromium, I make 3 moles of electrons. And then I'm using those 2 conversion factors we were given. 1 mole of electrons is 1 Faraday, and 1 Faraday is 96,485 coulombs. And then we're given the amps, and remember amps is in coulombs per second. So for every 2.75 coulombs, 2.75 coulombs pass in 1 second, 60 seconds is 1 minute, and 60 minutes is 1 hour. Then I'm able to solve, and when I solved, I got 14.0 hours as my final answer. So As you can see, dimensional analysis and stoichiometry are going to be really important for this unit as well. It's a little more complicated because we have all these weird conversion factors, but most of them are on your periodic table, so you should be able to remember them even if, you don't have to memorize them. Yeah. All right, that's electrolysis and Faraday's law, and really like electrolysis, stoichiometry, or dimensional analysis. All right. Feel free to email me if you have any questions. I would spend the rest of the class working on your skill builder and studying for your test. Next class is a review day, so start working on your what is that called? On your progress check in AP Classroom, and just get ready for your test. All right, have a good day. Bye, guys.